Hello and welcome. In a previous video, we took a look at the basics of vectors. And we took a look at a couple operations on vectors. That would be scalar multiplication, which is a fairly straightforward kind of multiplication, and vector addition. But what we haven't yet done is take a look at how we can multiply two vectors. Now there's a couple different kinds of multiplication we can use, and in this video we're going to be looking at scalar multiplication. You'll see why it's called that. More commonly though, we'll probably be calling it the dot product because that's really what the operator looks like when we write it down. So let's start off with the definition. The scalar product of two vectors, A and B, let's suppose those are in n-dimensional space, so they would have n components each. Well, we denote that here, as you can see, as A dot B. So that's where it gets this dot product name, and that forms a scalar, which is where it gets its scalar product name. So this is going to just produce a value that is in R. And the way we calculate that, A dot B is equal to A1B1 plus A2B2 plus A3B3 and so on, all the way up to the nth components, AN times BN. So we're really just multiplying corresponding components and then summing them together. So we can write that in summation notation as sigma from I equals 1 to n. That's just summing up all of the different terms from the first term to the nth term, and each term is given as A times BI, where I is the ith component. Let's try just a quick example here in three-dimensional space. This is a fairly simple multiplication operation between the two vectors. It's easy to calculate, and we probably don't even have to write down a lot of work here. A dot B is going to be simply just 2 times 3 plus negative 1 times 1 plus 1 times 5. So that'll be 6 minus 1 plus 5, and that gives us 10. Now, fortunately, that doesn't really get any more difficult, no matter what kind of dimension we're talking about. If you had 6-dimensional vectors, it's still pretty basic multiplication of direct components and then summing them all together. Well, let's take a look at a couple properties and maybe understand why the dot product is defined in such a weird way like this. For the purposes of these properties, let's assume that we have A, B, and C all being vectors in Rn. And here I've got each of those with a little vector symbol over the top, so you know that those are vectors. But maybe just be a little confusing, unfortunately, here. C often is something we use as a constant. So I have C in green without a vector over the top. That indicates that that is a scalar. Well, the first property to talk about, we say that this dot product, or this product, is commutative. That means that the order A dot B and the order B dot A produce the same value. And you can try to prove that yourself. You would just have to see that multiplication of each component is commutative, and therefore the scalar product of two vectors is also commutative. The next property is called the distributive property. Think about this as basically like distributing multiplication over addition in real numbers, except that here we're actually distributing a dot product or scalar product over vector addition. So it's very similar. A dot B plus A dot C. So you can see that that's essentially the same kind of distributive property that we get in real numbers. And you can also distribute from the right-hand side in a similar fashion because of the commutative property. Now at this point in time, another common property that we often see with normal multiplication would be the associative property. If I just had three scalars, A, B, and C, then A times B times C can be kind of taken to be in any order we like. We can take A times B and then multiply by C, or we can take B times C and then multiply by A. Now that associative property here doesn't really work with dot products because A dot B produces a scalar, and if we were to multiply that result by another vector C, that becomes scalar multiplication, not a scalar product of two vectors anymore. So we don't really have an associative property here, but we do have something that's kind of similar. This third property is that if we have a scalar multiple of A, and then we use the scalar product of that vector and B, so that would be CA dot B, then this order can be rewritten. We can take the dot product of the two vectors and then use scalar multiplication. Or we could also do a scalar multiple of b, and then take the dot product, a dot cb, and all three of those will give us the same result. Now, if you remember in the previous video, we also had the zero vector, and maybe this is a straightforward property to prove, but it's worthwhile writing it down anyways. The dot product of the zero vector and any vector a is equal to 0. But here, it's probably worth noting that we have the zero vector on the left-hand side, and here is a scalar. This is simply just the value 0, not the zero vector. Those are some of the basic properties to know, but that might still not quite enlighten you as to why the dot product is defined this way. There's other alternate forms of multiplication for two vectors. So where does the dot product come in? Well, maybe it'll be a little bit more obvious when we take a look at some of the applications of this form of multiplication. The first application is a very common one and very useful one if we wish to find the norm of a vector. Well, one way that we can find the norm of a vector A is by taking a look at what we get when we take A dot A. Well, component-wise, that would be A1 times A1 plus A2 times A2, and so on and so forth until AN times AN. Well, that'd be A1 squared plus A2 squared plus A3 squared, and that's exactly what we get inside the square root of the norm formula. So this gives us the norm of A squared. If we actually want to find the norm of A, then we would just rewrite that and say that the norm of A is equal to the square root of A dot A, or the scalar product of A in itself. That would be the equivalent formula of the square root of A1 squared plus A2 squared plus A3 squared, and so on. Now, I don't think we need to do an example of that. It's a very simple calculation, and we've already taken a look at finding the norm using the common formula. This is just a nice shorthand notation. But another application that is quite useful with the dot product, and also extremely common, is actually to find the angle between two vectors. Now, I'm not necessarily just talking about the angle on two-dimensional space, because that would be something we could easily visualize, but I mean actually the angle between two vectors in n-dimensional space. So just put these vectors in standard form, and they could be pointing in different directions all the way around the room in the three-dimensional space we live in. And this dot product actually allows us to find the angle between those two vectors. Let's maybe just take a look at drawing this as an example in two-dimensional space. Let's suppose here we've got the origin. And we'll start off with a vector A. Okay, vector A here in blue, and vector B, let's say, is going to be in red. Now, let's see if we can come up with a formula for finding the angle between A and B. This can be just labeled as theta. Now, to be clear, theta should be some value between 0 and pi. It's always going to be taking the smallest possible angle between A and B. The first thing we can do is actually use some properties that we're already familiar with, probably from geometry, and turn this into a common shape. We're going to turn this into a triangle. Now, I'm going to draw this as a vector here. Let's see if we can kind of come up with what we would call this vector if we already have an idea about vector addition. It's not A plus B. A plus B would actually be the vector from the origin way out to here. So it's not A plus B. But what we can actually see here is that B plus this vector in black here must equal A. We can even turn that into a little equation. B plus this unknown vector, we can call it X for the time being, is equal to A. Well, that's an equation just like any other. It just happens to be a vector equation. And we can still solve for X. That tells us that the vector X is equal to A minus B. And we can even also confirm that with vector addition graphically. If we take this vector B and negate it, and then use our tip-to-tail addition, we can see that that vector in black is in fact the vector A minus B. It's just not in standard position, but it is the same vector. So with that in mind, I'll just relabel this as A minus B. Okay, now we've got a triangle with three sides. A and B might be in standard position, although it doesn't really matter at this point in time. And A minus B completes the third side of a triangle. We're looking for the angle between vector A and vector B. Now, given two vectors, it's easy to calculate the norms of those. So we could easily find the length of the blue side and the length of the red side of this triangle, and we're looking for the angle in between. And if you think back to some previous courses in geometry, you might remember that it's actually a little bit tricky to get the angle between two sides whose lengths are both known. We have to use what's called the cosine law. I'll provide that here as a reference. The cosine law here, with the sides A, B, and C, and theta being the angle between A and B, well, then the length C squared is equal to the length A squared plus the length B squared minus 2 times the product of lengths A and B times cosine of theta. So let's use that here, and knowing that the lengths of each of these sides are the norms of those corresponding vectors, we can write this in vector form. The length of side C in our picture, well, that would be the norm of A minus B. And that norm squared forms the left-hand side of this cosine law equation. On the right-hand side, well, then the length A and the length B are simply just the norms of A and B. So making those substitutions on the right-hand side, we have our cosine law in vector form. Before we solve for theta, it turns out we can actually greatly reduce the complexity of this equation first by using that first application. And actually, it helps to know that A dot A is equal to the norm of A squared. So you see that on the right-hand side. We could actually rewrite that as A dot A. Same thing here. The norm of B squared can be rewritten as B dot B. But more importantly, on the left-hand side, the norm of A minus B all squared. Well, that can be rewritten as A minus B dot A minus B, and that's going to help us to reduce this the most. So let's focus on this left-hand side for a moment. From that first application, the norm of A minus B squared is equal to the dot product of A minus B and itself. And from here, we can use some of those properties that we took a look at earlier. Since we have a dot product and subtraction, which is just like addition, we can start using the distributive property. This vector A minus B is something that we can distribute across this subtraction of A minus B. By distributing the A minus B onto A and then onto the negation of B, we see that we have A minus B dot A minus A minus B dot B. Now let's use the distributive property one more time, but from the right-hand side. And you have to be a little bit careful here with some of the negations, since we have the negation of negative B dot B, that makes this plus B dot B. And one more property that we can use here right away is the commutative property. You can see that B dot A and A dot B are the same. And we can collect those two together, and that becomes a scalar multiple of minus 2 A dot B. And while we're at it, why don't we rewrite A dot A as the norm of A squared and B dot B as the norm of B squared? Okay, well that simplifies that left-hand side up very nicely. What we need to do now is we need to replace the left-hand side with everything that we've just worked on and see what happens to the resulting cosine law formula. For the time being, I'll just move this off to the side here a little bit, and we can then continue to work back on this equation. The left-hand side can now be rewritten as the norm of A squared minus 2 times the dot product of A dot B plus the norm of B squared. Now we haven't done anything at all with the right-hand side of this equation, so that can simply be copied into this next line here. Now let's see if we can work with that. On both sides of the equation, we have common terms that can be canceled out. That's the first thing that we can do to really make this a lot simpler. On the left-hand side, we simply have that dot product of A and B multiplied by the scalar negative 2. And on the right-hand side, the only term that doesn't cancel out is this minus 2 times the norm of A times the norm of B times cosine of theta. Now you can see how much easier it is to solve for theta. We can start, first of all, by canceling out the common scalar on both sides, minus 2. And then we can actually see that this is a new form of the dot product. This new form of the dot product is also worthwhile to memorize. This particular form is only very useful if we already know the lengths of A and B and we know the angle between them. So it may not be used quite as often as component-wise multiplication and then summation. But the main use of this alternate form of the dot product is really so that we can find theta. Cosine of theta is equal to the dot product of A and B divided by the product of the norms of each vector. Now, if you wish to solve for theta, when you take the inverse cosine or arc cosine of the value on the right-hand side, this will give you an angle between 0 and pi. All right, well, maybe let's try a quick example of finding the angle between two vectors outside of the realm of two-dimensional space. Why don't we try maybe in three-dimensional space? Now, I've got that alternate form of the dot product here written out on the top left of the screen, and then that equation solved for cosine theta on the right-hand side just for reference. Now, let's say we have two vectors, u and v instead of a and b, and u will be the vector 2, 1, 7, and v is the vector -3, 1, -4. Now, I'm going to point this out right now, maybe as a bit of a side note, but you're going to probably find that u's and v's look pretty similar, and they are also extremely common in multi-dimensional calculus and vector calculus. U and V, they're just, a slight difference in the way that they may be cursively written, so make sure to pay close attention there. I'll try to make sure that my writing holds up on these videos, but even in proper textbook notation, they're pretty easy to get confused sometimes. Now, we have to take a look at the dot product of these two vectors, u and v. That's a pretty simple calculation. We also need to take a look at their norms. So let's do that work first. The dot product or scalar product of u and v is simply just component-wise multiplication and then summation. 2 times -3 plus 1 times 1 plus 7 times -4. Okay, so that dot product gives us -33. Now we need to take a look at the norms of each vector, and those are pretty basic calculations as well. You can think about the norm of u as being u dot u and then square rooted. That would be 2 times 2 plus 1 times 1 plus 7 times 7. That gives us the square root of 54. And we might be able to reduce that radical, but it's not going to be that useful eventually since we're going to be taking the inverse cosine of all of this in a moment. Now for the norm of v, the square root of -3 times -3 plus 1 times 1 plus -4 times -4. And that gives us the square root of 26. Okay, now let's put all these values into the formula, and we can then take the inverse cosine. Now for convenience, when we have two square roots multiplied together, then we can take the square root of the product of their radicands. So we can multiply 54 and 26 and find that result and square root the entire value that way. Make sure to have your calculator in radians since we're going to be typically expressing all angles in calculus using radians. Now, this doesn't work out to be a very nice number. Theta is approximately 2.648 radians. Keep in mind that this value is always going to be between 0 and pi, so it has to be between 0 and 3.14-ish. Now half of that is 1.57. That would be like a 90-degree angle, pi over 2. So this would be an obtuse angle. It's going to be these two vectors aren't forming an acute angle, they're forming an obtuse angle, but they can never be forming an angle more than pi or 180 degrees. We would always consider the inside angle between the two vectors. Now, as you can imagine, a calculation like this also allows us to be able to find out when two vectors form a 90-degree angle, or pi over 2. That would mean that they are perpendicular. But there's a little definition here to point out. There's a small difference between what we call orthogonal and perpendicular. Now, as you can imagine, if theta is equal to pi over 2, then the right-hand side of this equation becomes 0, since cosine of pi over 2 is 0. Well, that would imply that a dot b has to equal 0. Well, that is what we commonly think of as orthogonality. The definition of orthogonality is the vectors a and b are orthogonal if and only if the dot product a dot b equals 0. Now, there's a small difference between that and what we commonly think of as being perpendicular, where the angle is 90 degrees. What's a little bit misleading is if the dot product a dot b equals 0, that doesn't necessarily mean that they form a 90-degree angle, because we already know the dot product of the 0 vector and any vector a equals 0. And the zero vector doesn't really have a definable direction. It's just a zero vector. It has no length, so it's really kind of impossible to say which way it's pointing. So we can say that the zero vector is actually orthogonal to all vectors. For a more common definition of what we think of as perpendicular, we just simply restrict the definition to be only for non-zero vectors. Two non-zero vectors, a and b, are perpendicular if the angle between them is pi/2 radians or 90 degrees. So not only can this alternate form of the dot product allow us to find the angle between two vectors, it's also a very quick way to find out if two vectors are orthogonal. And if they are both non-zero, then we can certainly say they're also perpendicular. There's a couple other results that come from this form of the dot product as well. A couple important theorems that we're going to be seeing again later on. The first of these theorems is the Koshi-Schwarz inequality. And that is that the absolute value of a dot b, that's not a typo, remember a dot b is a scalar, so we can only really take the absolute value of that. So that is a positive number, and that is always less than or equal to the norm of a multiplied by the norm of b. The right-hand side here, this is just simple multiplication of two real numbers. Now, I'll let you think about that, and with what we've covered already in this video, you should be able to come up with a very short proof of that. Once you've got the Cauchy-Schwarz inequality, then we can come up with a little bit beefier inequality called the triangle inequality. Now, what the triangle inequality states is that the norm of the sum of the vectors a and b is always going to be less than or equal to the sum of the norm of a and the norm of b. A little bit tricky wording there. And the reason why it's called the triangle inequality might be a little bit more obvious when we actually view this graphical addition. So we'll take the vector a and use tip to tail graphical addition plus b to get the resultant vector a plus b here in purple. What the triangle inequality says is that the length of this purple side is always going to be less than or equal to the sum of the lengths of the blue and red sides. No matter how the two vectors a and b are pointed, how they're oriented doesn't matter. So this doesn't matter if this triangle becomes an obtuse triangle or an acute triangle. No matter what kind of triangle they form, one side is going to have a length that is always less than or equal to the sum of the other two lengths. Now I say that this is a little bit of a beefier inequality because it's just a little bit trickier to prove. But again, using all of the theorems and properties that we've looked at so far, you should be able to do it. All right, well, let's take a look at another application of the dot product. And this is also one we're going to be seeing quite a fair bit in future calculus topics. We're going to be looking at what we call a projection of one vector onto another. Now, what we mean by that is if we're given two vectors, here I've got the vector a and the vector b, let's say maybe just in standard position. When we are looking at the projection of a onto b, then we are going to be essentially taking the tip of a and following a line that is perpendicular to the vector b, and our resultant vector projection will be this vector in purple. That's going to be always pointing in the direction of b, but you can see that its length is not quite the same as the length of a or b. Now that is only in the case where a and b have an acute angle theta. If the angle between a and b is greater than pi/2 but less than pi, then the projection of a is actually going to fall in the direction of negative b. So this purple arrow is going to be pointing in the opposite direction of b. You can think about it almost as if we have the sun here and it's casting a shadow directly onto the blue vector. It's casting a shadow underneath the vector a. So it's always going to have a length that'll be less than or equal to a. Now there's two formulas that we will wish to find out here. One is called the vector projection of a onto b, and that gives us this purple vector. That means that the result is a vector that has a magnitude and direction. However, it may be that we only wish to really find the length of that purple vector. Since we already might know which way it's pointing, we call that the scalar projection of a onto b. The notation PROJ with a subscript b A, that means that it's the vector projection of A onto B. Comp, or C-O-M-P, that's just the length of the vector projection. Now notice here that I say that that's not necessarily equal to the norm of that projection. This scalar projection is allowed to be a negative number, whereas the norm of any vector is always positive. In fact, this scalar projection is a positive number whenever theta is from 0 to pi over 2. It is negative if pi is between pi over 2 and pi. And it equals 0 if the vectors are orthogonal. And that would actually mean that the vector projection is also just the 0 vector. Now, the formulas to calculate the vector projection of A onto B and the scalar projection of A onto B are both fairly simple to come up with yourself. Basically just taking a look at a right angle triangle and using cosines. But we already know that that cosine between two vectors can be rewritten as the dot product. So both of these can actually be rewritten in some sort of formula involving the dot product of A and B. It's actually easiest to come up with the scalar projection first, COMP. The scalar projection of A onto B can be written in the form of the dot product of A and B divided by the norm of B. From there, we can come up with the vector projection of A onto B. We simply just need to multiply by a unit vector in the direction of B. And a unit vector in the direction of B is simply just B over its norm. So we take the scalar projection and we multiply that by B over its norm. However, in the bottom, that gives us the norm of B squared, and that is the same thing as B dot B. And so you'll probably be seeing the vector projection written in the form of the dot product of A and B divided by the dot product of B and itself multiplied by a vector B. So this becomes a scalar multiple of B itself. And that should make sense since the vector projection of A onto B is a vector always pointing either in the direction of B or negative B. Now, while both of these formulas are fairly easy to actually calculate, on its own, just finding the scalar projection or vector projection of A onto B or B onto A may not seem like it's overall that useful. But we will see it again in potentially some future videos, and we'll see that in some other topics as well, like optimization, for instance. One application is if we have a two-dimensional application where we have a line and a point. Let's suppose that point maybe doesn't lie on the line. If we want to find the shortest distance from that point to the line, well, that shortest distance should be perpendicular to the line. And we can find the length by using a projection technique. It's kind of a nice way to use vectors to solve what is otherwise kind of a geometric problem on the XY plane. So even this will become kind of a useful mechanism for dealing with two-dimensional applications. So that gives a pretty good overview of what the dot product is. It's a fairly straightforward thing to calculate, and hopefully you get a good idea as to why it's defined that way. It has all these applications, and one of the biggest ones is so that we can find the angle between two vectors, let's say A and B. That's going to help us out a lot when we're taking a look later on at multivariable calculus and functions in 3 and more dimensions. But for right now, you can just imagine that this is one of the forms of products of two vectors. We have another one coming up, so stay tuned. Thanks for watching, and I'll see you in the next video.